Okay, what I want to do now is talk about a couple more concepts related to the second law of thermodynamics. One of which that's very important is reversibility. Okay, when you think of reversibility, I want you to imagine a few things. First off, I don't know if you've ever done this before, but as a kid, I had one of those super balls. I loved throwing a super ball around, bouncing and stuff like that. And I remember if you had like in your kitchen like a hard surface, and you drop that super ball, if you just hold it, we're not talking about throwing it down. I'm just saying you hold it and you just drop it. It hits the floor, bounces up, and it almost gets back to your fingers. Almost. But it never does exactly to your fingers. It never reverse bounces right back to where you dropped it in the first place. But it's pretty darn close, right? Also, if you remember, if you swing on a swing real good, and you're swinging, and you just give up trying to work your legs and your body to swing up further, right? If you just stop and let yourself swing, you'll almost get back to where you swung before, but just a little short of that, okay? Both those processes are almost reversible, okay? Dropping a super ball and having it bounce up, it almost comes back to where you were. If you jump on a trampoline and you don't use any of your legs, you almost get back to where you were when you jumped. So it'll give you a big spring and a big jump back to where you were. And that's the key to reversibility is, can you go back to where you started without having any other inputs from the environment? Okay? Can you restore that? If it's reversible, you can go back from where you started without having any other inputs from the environment. Okay? That's reversibility. Okay, so why do we have this definition? The reason is that the most efficient processes, the best processes, thermodynamically speaking, are reversible. Okay? And reversibility is important because if we can find irreversibility, that is wasted energy. Okay? So that's wasted energy. That's energy that's not being used for what we want to. So what causes irreversibility? There's lots of things. Okay? I mean, this is not exclusive to these three things. But these three things are very common. Friction. If you have friction in motion, or I guess you could think of like air resistance is kind of like a friction, you know. If you have friction, you are going to cause irreversibility, okay? If you have something that slides on a very high friction surface, it's going to stop and you're going to lose that energy, right? Friction takes away energy, okay? So friction definitely causes irreversibility. Unrestrained expansion. Here's an example. Think about a balloon. Think you got a balloon, and let's say you open up the balloon and you let all the air out of the balloon. Is it real easy to get that air back in? Does the air just spontaneously jump back in the balloon? No, it doesn't, right? When you have that unrestrained expansion, if the air just goes out into the room, it's not going to come back unless you blow it back in or you hook it up to something that's going to blow it back in, right? That's not a reversible process. It just expanded and that's it. It's gone. Okay? And another one is heat transfer. Okay? If you have heat transfer, specifically heat transfer through a finite temperature difference, you can't bring that back. So if you have your coffee cup, this is again second law of thermodynamics. If you have your coffee cup and it's hot, and then all of a sudden it cools down to room temperature, the only way to bring that back is to put a heat source back in, right? It's not going to naturally just come back, right? It's not reversible. That's an irreversible process for that to happen. You can't just bring it back to the temperature it was before, okay? Those processes, when you have irreversibility, you have basically wasted energy, wasted useful energy. Now, you didn't really waste the energy, okay? Energy doesn't really get wasted, by the way, right? You can't really destroy energy. It's just transferred to heat. A lot of these to transfer to heat or to other things, and you can't use it anymore. It's not useful. Okay? When that coffee cup cooled down, you didn't really waste the energy. It just went into the air around us, right? And that's not very useful, right? Okay? So that's when you have irreversibility. That is basically a cause of inefficiencies. Okay? So we are going to look for things that are irreversible, and we're going to try to stop them. We're going to try to make processes as reversible as possible. Okay? Now, there's another concept here that's important. Internally reversible. When something's internally reversible, it's a process where there's no irreversibility inside the system boundary, okay? So what we're saying is, let's say we have some kind of boundary. It doesn't matter what it is. Remember, a boundary is just something we do in our mind. It's not a real physical boundary. This is just in our mind. We have a boundary. We can say that it's internally reversible if inside the boundary there's no irreversibilities, okay? Now, is there anything that's ever truly internally reversible? No, okay? But there's a lot of systems that come pretty close to that, okay? That inside the boundary, it's mostly reversible. It's really, really close to being reversible. So we'll say there's not, okay? There's not. So that we're going to model things sometimes as internally reversible processes, okay? We're going to say that inside the boundary, there was no friction, there was no unrestrained expansion, and there was no heat transfer inside. Now, there could be heat transfer to the outside. That's okay. You can still have an internally reversible process and have heat transfer to the outside. Just because it's internally reversible doesn't mean it's totally reversible, okay? Totally reversible means it's both internally reversible and externally reversible, okay? Now, all of this is probably going to confuse you at first, okay? And don't worry about that. You're probably going, I'm not really sure what you're saying there. I'm a little confused. That's okay, all right? We'll get there, all right? So it's okay to be a little confused by this, all right? What I want to do, though, is I want to talk about this thing called the Carnot cycle, okay? This is the first time we're going to talk about a cycle, but we're going to talk about a lot of cycles, particularly when we get to the last 3-4 weeks of the class, where we spend a lot of time on cycles, because really thermodynamic cycles are the heart of what we do. Your engine in your car is a certain cycle, okay? Power plants run on certain cycles. Refrigeration has a cycle. Lots of things run on a cycle, okay? And a cycle, remember, is something that takes a substance, does some different processes, and brings that substance back to where you started. If you don't come back to where you started, you're not a cycle, okay? Cycles come back to where they started, okay? So a Carnot cycle is probably the most important cycle, okay, that we're going to study. It's the ideal cycle for heat engines, okay? Carnot cycle represents the ideal heat engine cycle because it's made up of reversible processes, okay? Now, before I get started, no one has ever built a Carnot engine. No one's ever done it. It's kind of like the ideal. It's like the perfect, okay? No one's ever done it. Now, I hesitate to say no one will ever do it because there's been lots of things in time people have said won't happen, and they have, right? So I hate to say it won't happen, but let's just say it's unlikely, okay? Because it's pretty much perfection, okay? And I don't know about you, but I've never seen perfection before, right? I mean, in reality, there's no such thing as perfect systems, perfect people, perfect anything, right? Everybody has things wrong. Everything has something wrong with it, right? Nothing's perfect, okay? So there's no such thing as perfection, and certainly in thermodynamics, there's no such thing as this. But this is the best you can do, the Carnot cycle, okay? So now I'm going to go through each process. On the second page, what I'm going to do here is I'm going to write this process on a PV diagram, which you'll see why when we get to the end, why we do that, okay? Get to the end, you'll see why. So, yeah, specific volume. Pressure versus specific volume. We're going to start, by the way, we're going to start at state 1. You can put this dot right here, about right there. We'll say that's state 1. Just the general point right around there. That's state 1, okay? So what do? Let's go back to the first page and say, what's the Carnot cycle? All right, here's the Carnot cycle. The first step of the Carnot cycle takes us from 1 to 2, state 1 to state 2, and it is a reversible, remember everything's reversible here, it's a reversible isothermal, what does that mean? Yeah, constant temperature, expansion. Let me draw you a figure to help visualize this. Let's draw a piston cylinder. Okay, if we have expansion, that means the contents inside the piston, sorry, inside the cylinder are getting bigger, okay? The contents inside are getting bigger, but it's isothermal. It has a temperature, we're going to call it TH for hot, because this is at the hot side, okay? And we have surroundings. What's surrounding this cylinder here, what's surrounding it here is something that's been kept at a constant temperature also of TH, okay? Now, if you know anything about the first law, not the first law, I'm sorry, if you know anything about the ideal gas, when a gas expands, it wants to cool off, okay? When a gas expands, it wants to cool off. We're having expansion here, but it's isothermal, okay? That means it's not cooling off. What happens is, as this thing expands, it cools off super, super tiny amount. A millionth of a degree, right? Whatever. It's tiny, tiny amount, okay? And then what happens is the surroundings transfer heat in to the cylinder so that it keeps it at that constant temperature. So what you have is the surroundings at the same temperature as the cylinder. As this expands, what's inside wants to cool, but then the surroundings kind of put enough heat into it to keep it warm. Keep it that same temperature as it goes through. That's going to be a reversible isothermal expansion. Remember, reversible means we can take it back. I can easily go back from 2 back to 1, and it's all good. Okay, it's all good. So we can do the same thing. It's reversible. We can go back if we want to, and reversible means it's as efficient as it can be. Okay, that's stage 1. Let me show you what that looks like on our PV diagram. If you draw it up on the PV, it's going to probably look, I'm going to put 2 here, and it's probably going to look something like this. Okay? And all of this is at a temperature TH. Remember, it's isothermal. So 1 and 2 are at the same temperature. Okay? Yeah, there's a slight curve to that. Okay? All right, let's go on to the next one. Everybody see that? Everybody got that? Just it's like slight curve. It's kind of down and a little bit of a curve. I could have probably made it a little more of a curve, but it just depends. Okay. All right. The next process takes us from 2 to 3. This process is also reversible, but it's an adiabatic expansion. What does adiabatic mean? No heat transfer. What happens when you expand something, right, is that it wants to cool off. What you do here, very carefully, and this is hard to do, by the way, but what you want to do is as it cools off, the surroundings have to cool off with it, so there's no heat transfer between it and the surroundings. Okay? But what's going to happen is it's going to go from a temperature TH and it's going to go down to a temperature TL. It's going to go from hot to cold because it's adiabatic. There's no heat transfer here, but as you expand, it's going to cool off. But there's not going to be any heat transfer. Okay, this step is kind of impossible, really. The first step you could probably build the first one, reversible isothermal. You could probably do that. The second one is going to be a lot harder, but let's just say you could. We can come close, okay? So what does that look like on our PV? It's going to look like this. Again, there's like a little bit of a curve to this. Looks kind of like that, okay? And that's going to be state 3, and that's going to be a lower temperature, TL. Yeah?
So it expands.
Yeah, there's 2 expansions. There's an expansion that occurs without temperature change, and then there's another expansion that occurs without heat transfer. There's 2 full expansions, okay, inside. Remember, you might say, who cares about an expansion? But thermodynamically, expansions mean work. We like things, when they expand, that means we get work. That's good. Remember, work is integral PdV. I don't ask you to memorize too many equations, but I do ask you to memorize that one. Remember that? So when we have integral PdV here, that you see what I've drawn there? It's like an area under the curve, right? There's a curve, right? You can kind of see it. Okay? All right. Let's go back and do the next step, which is to go, now we got to reverse it. We got to go back. So now we're going from 3 to 4, state 3 to state 4, and it's reversible again. And now it's an isothermal compression. So this time, remember, I'm at the low temperature side. So I'm at low temperature. And what I'm going to do is I'm going to compress this gas. It's basically like air. I'm going to compress it, but as it compresses, it's going to want to heat up. It's going to want to heat up. But what I'm going to do is, as it heats up, I'm going to transfer that heat out. Okay? Because as I compress this gas back again, it's going to want to heat up. It's going to say, oh, I'm heating up, I'm heating up, I'm heating up. But nope, I've got the surroundings ready to absorb that heat, so it keeps it isothermal, constant temperature TL. Okay? Same thing, basically, as before, just the other way. What does that look like on my chart here? What that looks like on my chart is this. Probably something like this, 4. And I'm going to go, probably should have written that a little higher. Let's put that a little higher. Maybe there. Okay. And it's going to look something like this. And finally, obviously I got to go back to 1, or it's not a cycle. Something like that. Each one of those lines has a little bit of curve to it, nothing straight. So yeah, 4 is still TL because it's isothermal. Yeah, everything 3 and 4 is at the same low temperature, whatever that temperature may be. Okay. So obviously the final process here, you might guess, 4 to 1 is a reversible adiabatic compression. And what that does is it takes my temperature from TL back up to TH, the high. Because if you compress something and you don't have any heat transfer, it's going to have to heat up. Okay? That right there, that shape right there is the Carnot cycle. Now, you might say to yourself, okay, this is just something that the professor has shown me in lecture number 21 of thermodynamics, but I want to give you something here. I want to give you some context to the Carnot and tell you why it's so important. Let me show you something here on the web. Okay? Okay, you want to see that here? Yeah, there you go. Reversible, 4 to 1's reversible adiabatic compression. Let me give you some context here. Okay? Let me give you some context here. We got 2 more minutes, so hang with me for 2 more minutes. So let me give you some context. Reversible adiabatic compression, TL to TH. There's the Carnot cycle right there. Let me show you why that's so important. I'm going to go here to pi tau sigma. You may not have heard of pi tau sigma. What pi tau sigma is, by the way, it's at the Honor Society for Mechanical Engineering. Mechanical engineering has an international honor society. And when they looked at all of mechanical engineering and they designed a symbol to represent honors in mechanical engineering, what do you think they used? Yeah, does that look familiar? That's the Carnot cycle. Yeah. Now, when I went to school at Purdue, they had like a statue, like a little monument to the Carnot cycle. It was like right there, staring you in the face when you came out of the building. So, okay, that must be important. They don't make monuments of things that are just like whatever, right? They make monuments of things that are really important. So this must be important. It's what somebody thought represented all of mechanical engineering, the Carnot cycle. And I think it's, 1, because it is important, and 2, it represents kind of like the ideal. It's the perfection. It's the best, okay? That's really what the Carnot cycle is, okay? It's the ideal. It's the best. And so the principle here, this last thing, is that the Carnot heat engine is the most efficient heat engine, okay? You can't get any better. Can't spell. It's most efficient. And as you'll see next time, the Carnot principles also are going to be very helpful for us understanding how efficient something can be. And it helps us actually define temperature. So there's a lot of very, very important implications from the Carnot cycle. And we will do those next time. All right.